again. So let's go on. So please, next talk is by Vesselin Drensky, Institute of Mathematics and Informatics of Bulgarian Academy of Sciences. The title of talk is the Specht problem for varieties of Z sub-ungraded Lie algebras in positive characteristics. The result is joint work with Plamen Koshlukov and Daniela Martinez Carrera. Please, Professor Drensky.
Thank you very much. First, the organizers that they organize so nice meeting, and then the second for the possibility to give the talk. You see the title and the abstract. This is some results which will be, which are almost prepared for publishing. They are joined with Plamen and Daniela. But when I started to prepare the slides, that I decided that it's better to give a detailed picture, not only about this result, but the picture for the Specht problem. So from this point of view, my talk will be 54 pages of introduction and 2 pages of new results. So if you ask about the main problem in algebra, very naively stated, so I should start with this famous song of ABBA, I have a dream. So the dream is to describe, of course, all groups, all semi-groups, all ring algebras over a field, associated, non-associative, etc. But of course, this is hopeless. So we need some approach which is better. And the varieties of algebraic systems, this is something which has a very good advantage, that we treat in the same way groups, semi-groups, rings and algebras, commutative, associative, Lie, Jordan, etc., etc. And the idea comes from 2 papers which are old, more than 8 years old. One of them is the paper by Garrett Birkhoff about universal algebras, and Bernard Neumann, he has about something about groups, identical relations in groups, the first part. So, which are the 3 objects? If you have some class of groups, or semi-groups, or associative rings, or what you want, and you have some set, then there is an existing algebraic system in this class of groups, which is generated by X, with the property that for any object in this class, and any map from X to R can be extended uniquely to homomorphism. So such objects, they are called free algebraic systems in the class of algebras. They are freely generated by set X. And of course, when we write, when we work with the concrete class, and we want to mention that this is exactly this class, we should write f of this class instead of f of X. Then, this class, it has a very nice description, which is similar. I'll say this for associative algebras, although today this is a non-associative day, over a field K. So the free associative algebra, this is the algebra in polynomials in non-commuting variables. It can be unitary or non-unitary. So you have products of the variables. The order of the variables is important with some coefficients, and you have such linear combinations. In the case of non-associative algebras, you have something similar, but you preserve the brackets. So the identities, they are defined exactly in the same way. For example, if you have a class of algebraic system, you have all semi-groups or all groups or associative algebras or non-associative algebras over a field. And you have an algebra from this class, and you have 2 elements of the free object. Then you say that U is equal to V is an identity if it disappears when you replace this with all possible elements of the object. So in the case of semi-groups, of course, you need 2 things to be equal. In the case of rings, you can put everything from one side to have to be equal to 0. And the class of all objects which satisfies a given system of identities, it's called a variety, which is defined by these identities. Of course, you have the general notion that one identity follows from the other if it holds for all algebraic systems in the class which satisfy this identity. So if the variety has the same identities as an algebra from this class, then it's called that this is generated by this object. So this definition agrees with the following theorem of Birkhoff, which is known as HSP theorem. Why this is HSP? Because you have that a class is a variety if and only if it is closed under three operations: homomorphic images, subobjects, and Cartesian products. And of course, the variety is generated by a concrete object if and only if the class is obtained applying these three operations: Cartesian product, subobject, and homomorphic images. This is a little bit strange because in linear algebra, basis means that something which is minimal. But in the case of varieties, any set of defining identities of a variety is called the basis of this identity. And the variety is finitely based if it can be defined by a finite number of identities. Otherwise, this is infinitely based or not finitely based. And the finite basis problem asks whether every variety is finitely based. Of course, there is a weaker version. If the variety satisfies an explicitly given identity, the question is whether it has a finite base of identities. Of course, if there are varieties which are not finitely based, it's a good to give explicit example. So the problem was stated in 1937. If you translate this in a modern language, this is every variety generated by a finite group finitely based. This is in a paper by Neumann, which I already mentioned. And Specht asked this in 1950. A similar question. Okay, the original statement is a little bit different from what is known today, but in a modern language, the Specht problem is whether it's possible to define any variety of unitary associative algebras over a field of characteristics 0 by a finite number of polynomial identities. So this paper of Specht is with a very big influence. There are many results in this direction for associative algebras, and now the variety satisfies the Specht property if and only if all its subvarieties and the variety itself can be defined in a finite system of identities. And this notion Spechtian is not only for associative algebras, for all algebraic systems. Of course, you have a weaker version of the problem for classification of all algebraic systems. Again, I say this naively. So describe all varieties of groups, semi-groups, rings, etc., etc. But if the answer to the finitely based problem is negative, then this idea doesn't work because in many cases, if you have an infinite based variety, you have continuum many subvarieties. So this thing is on the meeting point with mathematical logics. I should say only two meeting points because there are much more. So you can restate this in the language of mathematical logic as the problem whether the system of the identities is finitely axiomatizable. And there is a problem by Tarski. Is there an algorithm which, given an arbitrary finite algebra R as an input, the algorithm determines whether the variety is finitely based? So this is a paper in 1966, but Tarski attributed the problem to Perkins in his thesis in Berkeley. The answer was negative because Mackenzie much later showed that he started with a Turing machine and get an algebra which is finite, a finite so with finite kind of operations, so that the Turing machine counts if and only if the algebra has a finite basis of the identities. Of course, here immediately it follows that the problem cannot be solved algorithmically. And there are some more things in a paper by Perkins, quite odd. And I'm not sure, but I think that this problem is still open, for example, for finite semigroups. Now I start with some positive results. The first thing is using structure theory of groups and algebras. A typical result, that the identities of any finite group, finite associative ring, or finite algebra, finite Lie ring or algebra, or finite Jordan ring or algebra, all these objects, they have finite basis of the identities. Here, in the case of Bertulin and Olshansky, the proof uses also theory of quasi-varieties, and the other, they are simply structure theory. There are the papers, the paper by Schwartz and Powell, the paper by Kruse and Goff for associative rings, Bertulin and Olshansky for Lie rings, Medvedev for Jordan rings. So I state again that there are much more results. So here there are some examples. And the next method, this is the method of Higman-Cohen. This is based on a paper by Higman, which was published 81 years ago. And Cohen used this 15 years later. And this method is based on something which I give simply some idea. You consider finite sequences of non-negative integers, and you say that one sequence is less than the other if the first sequence is majorated by a subsequence of the second one. Then the statement which follows from the result of Higman is that such sequences satisfies the descending chain condition, and any set of sequences has a finite subset of minimal elements. So in the general case, there are different versions using this fact. And Cohen applies this to show that with abelian varieties of groups, they satisfy the Specht property. So here you have some positive results which use this technique. Some of them are for groups. I said here very few. Result by Michael von Lee, by McCain, his thesis, Garashina in Moscow. For the algebras, there are Bryant and von Lee, Kane again. For associative algebras, this was the main tool before Kemmer. So again, I say few results also by Watishev, Genov, and Angel Popov. And then they proved this for varieties of associative algebras which satisfy product of commutators. Then there are some methods of commutative algebra. For example, for Lie algebras in characteristic 0, Krasilnikov showed that the finite basis properties for varieties which are product of commutators of length 2. If you have bicommutative algebras or bicommutative superalgebras in characteristic 0, and in the general case, you use methods of commutative algebra, and also you use some in characteristic 0, you combine this with some ideas from representation theory of classical groups. There are two papers. One of them is with Zhachaev, and the other is with three more colleagues from Kazakhstan. Then there is another notion of weak polynomial identities. Weak polynomial identities, originally they were introduced by Razmisov, and you have an associative algebra, which is generated by a vector space, and you consider polynomials in the free associative algebra, which vanish when you replace them from the elements of the generating vector space. And the consequences of the identities, of the weak identities, you're allowed to replace the variables with linear combinations of the elements in the vector space. And of course, if the vector space has a structure of a Lie algebra, for example, you're allowed to substitute also elements of the free Lie algebra, which is a subalgebra of the free associative algebra. Okay, you know that, probably all of you know that the weak identities, they were introduced by Razmiswov, and he used this for two things. One of them was to show the existence of central polynomials for matrices. His method was different from the other proof of the proof of Formanek, and the other is to find the polynomial identities of 2 by 2 matrices in the Lie case and in the associative case, in the case of characteristic zero, of course. And there is one more application. Volichenko, he proved a paper about 40 years ago, showing that a product, a commutator of 3 commutators of length 3 in the Lie case, in characteristic zero, this is Spechtian. And the key moment of the proof was that if you consider the triple commutator as a weak polynomial identity, it satisfies the Specht property. Of course, one of the big achievements in this direction was the structure theory of T ideal developed by Kemmer. In characteristic zero, he developed structure theory of T ideals of the free associative algebra in the spirit of the classical ideal theory for polynomial algebras. And he combined this with some application of superalgebras. Okay, he had many important results, but in our case, one of the important results was the positive solution of the Specht problem. So there are several papers here, and there is a book which was translated of the Doctor of Science of Thesis of Kemmer, translated in English. And also, there are 2 more recent books by Kanel, Beloff, and Troen, and the second part was with Karasik, which discuss in detail the results about the results of Kemmer. And also, I want to state that the Specht problem is still open for varieties of Lie algebras over a filtered characteristic zero. So this is something which is. And again, if you speak about counterexamples, the list is quite long, and there are many results which are not mentioned in the talk. So the easiest example is when you study non-associative algebras. For example, binary magmas. So this means elements with one binary operation, which is non-associative, or in Navius 18, these are non-associative semigroups, non-associative rings, non-associative algebras over any field. So you have product of 2 products, then you put here some elements of first degree, and then you have a product again. So here the brackets are left norm, the product. So you have x, y, z. This is x, y multiplied by z. So this is easy to see that in this case everything is as it should be. If you have a finite algebraic system, again the list is quite long, but you can ask what is the minimum number of elements in the finite system which guarantees that there is a infinite base variety. For objects with 2 elements, the answer is positive, and for 3 elements, there is a counterexample. There is this is the table with the multiplication rule, and it's known that this object has no finite system of identities. And you can see, of course, the proof in the paper. I don't want to discuss this. Also, Lvov he suggested a construction of non-associative algebras. You have a vector space and 2 by 2 matrices. The vector space is 2-dimensional, and the matrices they act from the right, and the multiplication is in this way. So this algebra, it satisfies the identity for left nilpotency. And it turns out that this 6-dimensional algebra, it has no finite basis of identities. You can even go further. You can take a 2-dimensional vector space and 2-dimensional elements in the free associative in the matrix algebra, and again, this thing has no finite basis of identities. So for semi-groups, the first counterexamples, they are in 1965. These are the identities which guarantee that there is no finite basis of identities. Almost in the same time, there was another paper with another system of identities. And in 1985, there was a paper by Chevron and Volkov. There are more than 40 other examples of varieties which are not finitely based. So, and I simply want to mention some fact that if you consider semigroups with 6 elements, there are 15,973 distinct semigroups. So this is up to isomorphism or anti-isomorphism. And 1,373 are monoid, so they have unit. And from this big amount of semigroups, 4 are not finitely based. 3 of them are monoids. And the other semigroups with 6 elements, they have a finite base of identities. You can see the papers where this is proved. One of them is a PhD thesis. The other is, so this is something which is a lot of work, of course, to show that these elements are. And also, for groups, the first example, this is by Olshansky in 1970. He showed that there are continuously many varieties of groups, and hence there are infinite-based varieties. And the first explicit examples there were by Sergei Ardian, who used his approach with Novikov about the Burnside problem and the negative solution of the Burnside problem. Then in the same time, there was an easy example by Vaughan and Lee. These are the system of identities which are not finitely based. And also you have that 2 more identities, the exponents 16 and a commutator of 3 commutators to be equal to 1. And here again, the commutators are left normed. And there are simple examples by Kleiman in Russia and Roger Bryan in England, that the variety before A2, which means that the groups there, they have a normal subgroup, which is a big enough exponent 2, and the factor is of exponent 4. Then the variety has such a basis of identities. So you have product of squares in degree 4 equals to 1. Here, you cannot define this system by a finite number of identities, but of course, each identity implies the previous one. For example, here, if you put x1, xn to be equal to 1, you get the previous one. And there is something which is known as continual hedgehog. Hedgehog, you know that this is an animal with a lot of figures. So there are continually many pairwise different varieties of groups, such that if you intersect 2 of them, you get the big something which is in the Abelian variety. And this intersection is the same for all intersections. And there are more examples. For example, there is a survey paper by Gupta and Krasilnikov, published 20 years ago. So the Lie algebras, now I'm closer to the topic of my talk. So in characteristic 2, the first counterexample was by Michael Vaughan Lee in 1970, is that the variety of Lie algebras over a field characteristic 0 defined by this identity is the first identity. This is the so-called central bimetabelian identity. This variety is not finitely based. Again, the commutators are left now. And the second thing, which is also quite surprising, that if the field is infinite of characteristic 2, then the 2x2 matrix is considered as a Lie algebra. They have no finite base of their polynomial identities. So, and Igor Burichenko, he added one more identity to this system, and he showed that he obtains a variety which is locally finite. Locally finite means that the finitely generated objects are finite dimensional. And also this variety is limit or just non-finitely based, which means that it has no finite base of identities, but all proper subvarieties, they have finite bases. And in my PhD, this is in Moscow, I found a basis of the polynomial identities of the Lie algebra in characteristic 2 when the field is infinite. This is the basis. To the identities of Vaughan Lee, we added one more series of identities. Okay, this was in my thesis, and it was not published in another paper. And the paper and the thesis was somewhere in the libraries. And Lopatin, he found the same result with a proof which is a little bit different, but similar to the proof. So this was in archive, but when Lopatin knew that this is my thesis, he never published this more. And there is a problem which I want to state, that there is a simple three-dimensional Lie algebra. So this is similar to the case when you have the three-dimensional vector space and the vector product. If the characteristic is 2 and the field is infinite, is the base of this polynomial of the identity finite. So this is simply to see what happens. 2x2 matrices, they are 4-dimensional, and the algebra is solvable there because the characteristic 2. And this algebra, this is simple, and maybe it's interesting to see whether it's finitely based or not. Also, Vaughan Lee, he had another example. His variety, it has a product of its commutator of 2 commutators of length 3. The identity is the series of the identities of this form here. So you have, after the commutator of length 3, you have x1, x2, x2, x3, xn minus 1, xn, and then you close the circle xn, x1. So this system is not finitely based. And again, although he didn't state this explicitly, the key moment of the proof was that if you consider the weak polynomial identities defined by the commutator of rank 3, and this product of n commutators of rank 3, this is not finitely based. And of course, you can ask after this, what happens with this weak identities in characteristic bigger than 2? If the answer is, if you have a counterexample here, you should have some counterexample similar to this counterexample in characteristic P. So in characteristic P bigger than 2, I had a paper. The result was obtained independently by Kleiman, that if you have the variety which is of this form, this is solvable of class 3. So you have commutator of commutators, etc., to have something of degree 8. And you have this system of identities. This is not finitely based. And the result of Kleiman was similar because we both used the ideas of the paper by von Lee. And it turns out that if you add the angular condition, we obtain a variety which is infinite based, but it's locally finite. And also another result from the previous paper in Algebra and Logic in 1974, that in the case of infinite field of positive characteristic, there is a finite dimensional algebra with not finitely based of its polynomial identities. So this algebra satisfies identities similar to this kind of identities. And for associative algebras in positive characteristic, the first counterexamples were given by Belov and a little bit later by Grishin and Shigolev. In that time, Victor Nikolaevich Latishev, he had a seminar, and these three talks, they were in three consequent meetings of the seminar, but Belov had the first one. So, there are also some other papers. Belov, for example, his paper, this is translated in English. Grishin, he has also something in English, because for many people, the papers in Russian, they are written in a rare language, as the same way as the papers in German or in French. Okay, and the simplest example is in characteristic 2. There are in two papers by Gupta and Krasilnikov. One of them is for new algebras of index 6, and the other, there are such things, they are simple identities. And there is a conjecture here that if you have an infinite field of characteristic 2, then the 2 by 2 matrices, they have no finite base of their polynomial identities. The problem is that in the Lie case, this was established already by von Lie, but there you have only commutators, and here you have more consequences, so, and more identities, of course, which are not Lie. And now I go to graded algebras. So, for example, you have a group, you have an associative algebra, and it is G-graded if this is a direct sum of vector subspaces, which are indexed by the elements of the group. And the condition is that if you take the product of two graded components, you get another, you are inside another graded component, which you preserve the grading here. And of course, you can find the free graded associative algebra. So its generators are also graded by the elements of the group. But of course, you can speak about graded identities, where the condition is that when you replace the elements, you replace the element with the corresponding, from the corresponding graded components. In the same way, you can define graded Lie algebras, you can define graded Jordan algebras, and other non-associative algebras. Here, in my case, when I speak about grading, we preserve, you keep the usual multiplication, because if you have Lie superalgebras, the sign of the multiplication depend of the grading. Here, the condition is that you preserve the same multiplication. So, in the same way, we can consider the Specht problem for G-graded elements. And in characteristic 0, and the finite group, you have an analog of the result of Kemmer, that if you have a G-graded associative algebra, it has a finite base of these G-graded identities. So the proof uses the approach of Kemmer, but with new moments, because there are some difficulties arising from the grading. This paper was published, this is by Sviridova, in the case when you have a abelian group, and almost in the same time, by A.R. Jelev and Alexei Kanopilov for any finite group. But the papers, they were submitted in the same time. So they were obtained independently, and each paper cites the other paper. So in the case of matrices, there is the so-called canonical grading with Zn. These are the elements which are the integers modulo n. The condition is if you take the matrix unit, you have that the difference j minus I, this should be k modulo n. These are the homogeneous components. And in the case of two variable, 2 by 2 matrices, if y and okay, this and z are the even and the odd components, then over an infinite field, there is the basis of the algebra, of the Lie algebra, which is Z2 graded, consists of these identities. This is not finitely based. So you have the commutator of two even component is 0. If you have two odd components, this is already in the center. And you have here two odd components, and between you have many even components. And also, if you add here an identity that odd even is 0, then we obtain a limit variety, which is from one side this is finitely based, infinite based, from the other side this is locally finite. And this is some paper by Kushvukov, Krasilnikov, and Silver. Now, if you consider the upper triangular matrices as an Lie algebra with the corresponding canonical Zn grading, when the field is infinite, the basis consists of such identities. The 0 components then commute because they are on the main diagonal of the matrices. And if you have two components such that the parity is bigger or equal to n, then you get 0. This is a paper by Kusvukov and Yukihide, published 6 years ago. And in characteristic 0, or if the characteristic is bigger or equal to n, then the Z graded algebras generated by and by upper triangular matrix, it satisfies the Specht property. But in the case of characteristic 2, then the Z3 graded identities, there is a system of Z3 graded identities which is not finitely based. This is in a very recent paper by Daniela Martinez-Correa and Plamen Kushvukov. And now I go to the new results with Plamen and Daniela. So we consider the Zn graded Lie algebras defined by the Zn graded identities to commutator. The commutator of even of 0 component is 0. A commutator of 2 components is 0 again when the sum is bigger or equal to n. Of course, when the field is infinite, the above identities, they define the variety generated by the Lie algebra of upper triangular matrices with the canonical grading. And now assume that the field has a positive characteristic P. There is a subvariety defined by these identities, which is similar from one side to the identities in the case of characteristic 2, what we had before. This identity here. And from the other side, this mimic the case of our identities in my paper from 1974. But here we had commutators of length 2. But here, because of the grading, we don't have commutators, we have only one element of degree 1. So from one side, this extends for the case of odd characteristic the result of Daniel and Plamen in the case of characteristic 2. And the second one is that if you add to this variety the angle condition that if you commute p times with a zero component, you get 0. This variety is locally finite and doesn't have a finite number, a finite base of the polynomial identities. And also, when the field is infinite, this variety contains a Lie algebra which is finite dimensional, and it's ZP plus ungraded, and its polynomial identities are not equivalent to a finite number. Again, these results, they are graded analogs of the results for Lie algebras, which were obtained by von Lie, by me and Borychenko. And also, there are 2 papers by Kushvukov, Krasilnikov, and Silva, and Martinez, Correa, and Kushvukov, which I mentioned before. They contain more results on the Specht problem for graded polynomial identities. So I think that I finished here.
Thank you very much, Professor Drensky, for a very detailed survey and very interesting new results. Thank you. So please, any questions or remarks?
Okay, I have many years ago, there was a joke which is based on nothing, but nevertheless it was very popular. The paper by Bernard Neumann, where he asked the finitely based problem for groups. It was the first part of a paper which didn't have a second part. The paper of Specht, when he asked it, the Specht problem, it also had a first part and no second part. And the people joke that they expect that in the second part of the paper, they solve the problem. Of course, there are no reasons for this, but there was a joke.
Okay, thank you. Dear participants of our seminar, do you have some questions? If no questions, let us thank Professor Drensky for a very interesting talk. Thank you very much, Professor. Now we have a break and start exactly at 9 o'clock by European time. Thank you. See you in 17 minutes.